Right, so I'm going to walk you through the basic functionality of this MFJ 868 giant SWR slash watt meter. I'm troubleshooting one of these that is belongs to a friend of mine that stopped working on him, and I am going to repair it. Now, these things are crazy, crazy simple. In fact, I'm going to go down to the schematic, and I'm going to show you pretty much how this thing works. Now, I understand it largely. There's one little piece of it that I don't quite get, but that is not going to be a factor for what we're working on here. Let's get this thing where we can rotate it. I don't know if you can do that here. Let me do this. Let me open with whatever. I want to rotate the page to look at the schematic a little easier. Yeah, open my file, whatever. You're getting ready to be annoying. Wow. All right, here we go. PDF is loading. All right, let's scroll down and see if we can spin this page to the side. La la la, schematic. Can I rotate it? I want to rotate it. There we go. Perfect, 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 perfect. Okay, so let's walk through this unit. So I said it's crazy simple. Basically, every SWR meter is nothing than a voltmeter. You're going to be measuring forward and reflected power off of an RF transmission line, and you're going to essentially display either the voltage levels or a ratio based on the forward power compared to the reflected power, what we call the SWR, the standing wave ratio. But essentially, this is a voltmeter. Now, it is a microvolt or millivoltmeter because you're talking really, really small numbers here. But in essence, it's a voltmeter. So let's walk through how this thing works. The unit here can be powered either via a 9-volt battery or by a 12-volt DC barrel jack on the back. There's also a backlight on the unit. However, the backlight only works when powered off of 12 volts. That is by design. In fact, I can show you why that is here in the design as we go through it. So, 12 volts over here on the right-hand side. The 12 volts comes in. Your ground obviously is tied to ground. And you've got a lead here going to your on-off switch. Your on-off switch is obviously going to control whether the unit is being supplied power or not, but it's also where we hook up the lamp. So we've got a set of wires here, LP plus and LP minus, that basically get power when the unit's turned on and turn on the backlight. There's D3 here, which is a 1N4007. That is basically a polarity protection diode, but it's also serving, well, I'm not going to say that. I don't want to mislead you. It's a polarity protection diode so that if you accidentally hook this thing up backwards, you're not going to blow the rest of the unit. So DC volts comes through. We've got some filtering caps here to smooth ripple, and this is plus 12. Now, plus 12 is kind of a bad description, and I'll tell you why here in a second, but let's, for the sake of argument, just call that VCC or VDD. That's our voltage rail. Now, let's say that I didn't want to run this thing off of a 12-volt barrel jack, but I wanted to run it off the internal 9-volt battery. How would I do that? Well, here's the 9-volt battery connection. We've got minus to ground, which is obviously common with the 12-volt supply. Here's your power switch again. Same switch, different poles, but same switch. And we've got a little PNP transistor. Now, the way a PNP transistor works is when a little bit of voltage, or I shouldn't say voltage because it's not voltage driven. A BJT is current driven. So when a little bit of current comes from the emitter towards the base, and this base is tied, essentially down here towards ground, when current can flow from the emitter to the base, the transistor will turn on and it will allow voltage to then flow across to the collector on a PNP transistor. So essentially what's happening, we turn this thing on, comes across, and we get 9 volts here. So that's why I said we don't really want to call this plus 12. It's just VCC. Now, that's the other job this diode is doing, is it's protecting us. It's keeping us from feeding that +9 back towards this 12-volt source. So either way, whether we're coming from the right on the 12-volt input or we're coming from the left on the 9-volt side, we're going to have our VCC show here at the +12 rail. So bad naming convention, but that's what it does. Now, there's a little circuit here, and I partially understand how it works. I don't fully see it. I think it's just a problem with me visualizing it. But what this little circuit is doing is it's looking at the forward power. So basically, when you're transmitting through the RF transmission line, we have a little bit of current coming up here. And we've got a current limiting resistor here. A little bit of current that is going to apply a current, I should say, to the base of this Darlington transistor. This is basically just a high gain NPN transistor. Now, most of the time, this thing's pulled to ground, so it's always low. When we put a little RF through it, we drive it high. When we drive it high, something about this logic, oops, let me get rid of that. Yes, it's fine, whatever. Something about this logic that I don't fully understand is essentially allowing 9 volts to flow up here. So this is kind of, I think, preventing 9 volts from just flowing through this transistor normally unless we have RF here. So essentially it's a power saving feature. So only when RF is going through the unit do we apply VCC. Now what's that do downstream? Well, it's easy. There's only like one thing here that runs off of VCC, and it's this quad op amp. So you've got a TLC 2274 op amp, which is a quad op amp, an operational amplifier. 2 of the op amps in it are just grounded, so you've got the inverting and non-inverting inputs just tied to ground, so they're just kind of sitting here doing nothing. But let's walk through what the rest of this is doing. So we've got our forward and reflected power. You've got a switch here to select forward and reflected power. So we're going to use that switch to decide which of the 2 voltages we want to detect. We're going to bring that voltage in through a switch. We've got a power and an SWR switch here. Forget that for the moment. It's not important to understand what that's doing. Just suffice it to say that that has to do with calibrating the meter scale through the use of this resistor. But that's not important for understanding what we're trying to describe here. So voltage is going to come through the switch up here. And we've got this little 3-position selector switch. This is basically where we're going to say 20 watts, 200 watts, or 2 kW. And really all the difference is it's if it's 20 watts, we're going to follow this path here. If it's 200 watts, we're going to follow through this trimmer that we can do some tuning on. And if it's 2 kW, we've got a current limiting resistor in here and another trimmer. So this is just all about scale calibration. So we've got our voltage right here. Voltage comes through here, boom, 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 hits the non-inverting input of our op amp. So what's that mean? Well, the short and skinny of it is it means that this op amp, as part of our IC, remember there's 4 of them in there, is going to be amplifying the signal. It's going to be amplifying voltage. Now, we're not going to get into the math to talk about how much it's amplifying it. It doesn't matter for the sake of this conversation. Pin 14 here, we're going to have voltage coming out. So we've amplified the signal. It's coming out. Well, that's going to be a high signal. So it's going to take this D1. We're going to pass through diode 1. And we're going to be applying a current. I got to say voltage. This is not a FET. This is a BJT. We're going to be applying a current to the base of this NPN transistor. So what happens when you apply a current to the base of an NPN transistor? Well, you allow current to flow from the collector to the emitter. So here's the collector. Here's the emitter. So you notice where this collector's at? It's at +12. So when this op amp passes voltage through this diode and the current hits this BJT, we're going to allow +12 to poo through here and come out this way. This little switch circuitry here, this is just part of your peak/averaging logic, so don't worry about that. But follow the signal here. We come to another op amp. Now, it's the same chip. It's just a second op amp inside the same package. So we're hitting the non-inverting input, amplifying the signal, and we come back out. Now, you'll notice we've also got +12 here. Now, this +12, again, it's that same VCC line. And in fact, if we're running off the 9-volt battery, it's not +12 at all. It's +9, just like it's +9 here. It's just VCC. That's actually powering the op amp. So, short and skinny, op amp through 2 stages is amplifying the DC voltage. And voltage is coming through here. This is a little resistor for calibration, and voltage is working its way down here. Boom, out to this switch. When the switch is on the power setting, we are going to be passing that voltage out to meter plus, and then meter minus is ground. So that's your complete circuit walkthrough of basic SWR measurement and power measurement on this unit. So if you're doing SWR, this is actually a little simpler. So we've got your forward and reflected power. You can choose either of those. But then you've got your power SWR switch here. So if we're in SWR mode, the voltage, either forward or reflective, is going to come in. We've used this resistor to calibrate the scale, if you will, on the meter. And then we're passing DC voltage through here. We've got the SWR switch position. If we're in that position, it goes out this way and again hits the meter. And the meter is calibrated and has markings on it, and it's going to tell you what the standing wave ratio is. So pretty straightforward. So that, in a nutshell, is this MFJ 868 SWR meter. Now, this unit has failed, and I know that at least the op amp has failed. The reason I know the op amp has failed is because when I applied 12 volts right here, where I should have been applying 12 volts, there was magic blue smoke leaving the op amp, which tells me the op amp's got issues. So what we're going to do is we've actually pulled the chip off the board. We're going to be replacing it. The board was actually laid out with both a dip package and an SMT package. And since popping a chip in is a lot easier than soldering onto an SMT package, we're going to put a socket in here and replace the chip with a dip variant. So in the future, either immediately while I'm diagnosing the rest of the circuit, or down the road, the chip were to fail again, we just pop it out, pop a new one back in. It's a lot quicker than doing a full-fledged repair. So easy stuff. So what do I think's wrong with the unit? Well, there's not that much to go bad here. So I'll tell you first, up in here, there ain't nothing wrong up in here. This is all working because I'm getting 12 volts out through this diode. So this diode's good. I've checked it. It's not shorted. It's not, whatever. I'm getting 12 out here. So that's good. This I could care less about because it has nothing to do with my 12 volt source. And I'm not testing this whole 9 volt side of things. I'm just using the 12 volt input. So this has nothing to do with it. None of these passives have anything to do with it. This little Darlington's not going to have anything to do with it because, again, that's only controlling the 9 volt side. So all of this stuff, the only thing I really care about is that I'm getting 12 volts through here. So we're good there. Everything else is just about, these are all passives, so nothing here is going to fail. We've got, one quad op amp. You've got a diode. I've already tested that diode, and it's passing the diode test just fine, so I don't think that diode's having any issues. I've got an NPN transistor here. That's like a nickel. And I've got like a $2.50 op amp. So even though I may not know why the op amp fried, it definitely fried. So we're going to swap out the op amp. I might swap out this 3904 because it's a little nickel NPN transistor that I've got 2,000 of in the drawer anyway. And that's it. I mean, there's no other reason that this meter shouldn't function. So that's the plane of attack. That's what I'm seeing. That's a little bit of a tour of the schematic and a walkthrough of how this MFJ 868 watt meter is designed. Hopefully this has been informative to you. Hopefully I don't sound like a blubbering idiot, but if I do, that's okay. I'm just a hobbyist. I do this for fun, and I'm always learning. See you guys later.